vibration, we can describe it a number of ways. And there are another number of properties for waves. Was there a question? I thought I saw a hand.
No, sorry.
Okay, just out of the corner of my eye. So we have many different kinds of oscillations. And a good example is like with a spring. We can have what are called transverse oscillations, up and down. And so let's see. Colton, could you help me out with this one?
Yeah.
Or Braden?
Yeah.
If you could head down this aisle here. And let's try it with the colored spring first. Don't have to go very far. Just on the table. If I do like that, we have what's called a wave, a disturbance. It moves, from me to Colton and then back again. But by moving it to the side, the displacement of the coils is side to side, yet the wave, the disturbance, clearly moves from me to Colton. You see that? So we call this a transverse wave because the motion of the material is transverse or perpendicular to the direction of the disturbance. So the disturbance moves from me to Colton or Colton to me. And if the displacement is to the side, we call that a transverse wave. Now, contrast that to that kind of disturbance. Think of this as like a compression wave. We call this a longitudinal wave, where the displacement is along the direction of the disturbance. So the displacement of the medium is back and forth as opposed to side to side. Does that make sense? So this is a longitudinal wave. Go ahead and give it up, Dr. Fry. Yeah, you clearly see some sort of disturbance moving from Colton to me and back. And that's because each individual coil is moving back and forth along the same direction as motion of that disturbance. Where a transverse wave, it's perpendicular to that or transverse to that, to the side. Okay, go ahead and let go. And so we can have either transverse or longitudinal waves. So for example, can someone tell me what like a wave along a string is? Like a guitar string. If you pluck a guitar string, do you get a transverse wave or a longitudinal wave?
Transverse.
Transverse. What's your name, sir?
Jared Gibson.
Okay, that's right. Because the displacement is back and forth. The disturbance will go up and down the guitar string, but the actual displacement of the guitar string will be side to side. How about sound waves? You can hear me now. Is sound a transverse or a longitudinal wave?
Longitudinal.
Who said that?
Crystal, she's.
Okay. Yes. In a longitudinal wave, it's basically a wave of compressions and rarefactions, where when you speak, you squish the air, make it more dense, and then it's like you've seen a speaker. A speaker physically will move back and forth. It'll squish the air and then pull it back, causing a compression, then a rarefaction. And you'll get this, you can think of the sound wave as like a pressure wave where the pressure varies from point to point. It'll go up and down, slightly above and slightly below atmospheric pressure. Or you can think of it as a displacement wave, where the molecules in the air are physically displaced one way and then another way. They'll actually oscillate back and forth. And that displacement is longitudinal along the direction of the propagation of the sound wave. So sound is a longitudinal wave. Waves on guitar strings and piano strings are transverse waves. What about waves in water? Are those longitudinal waves or transverse waves? Sorry?
Transverse.
Transverse, in that the waves go up and down? Sir?
I would think transverse as well, because you can't really compress water.
Okay, well, you see the physical water, but moving up and down. So if you had a cork out in deep water, you'd see it bob up and down. Ma'am, what's your name?
Lauren Smith.
Sorry?
Lauren Smith.
Okay. Sorry, it's kind of hard to hear, for me to hear inside this cone of silence.
Oh, you're okay.
Sir?
Josh Crossgrove.
Okay. And the masks always make it fun. But what about right near the shoreline? I mean, out in deep water, we'll see the cork go up and down. But when waves come onto shore, do you see corks moving back and forth? Yes, you do. Thing about water waves, and with a lot of other waves, is they're mixed. They have both longitudinal and transverse components. So you can have transverse, longitudinal, or mixed. And for example, in water, if you look at any little chunk of water, say if there's like a little piece of weed out there in the water, not right at the surface, or even at the surface, that weed will, if it's deep, tend to move more up and down, and where it's shallow, move more back and forth, but in all cases, it'll move it on an ellipse. You'll either go like this, as I'm tracing my finger, up and down, but also back and forth, or if it's shallow, it'll tend to move in more of a elongated ellipse, still up and down, but also back and forth. So you could have either waves. And we could talk about S&P waves in earthquakes. Are folks familiar with those waves? Maybe you've had a geology or an earth science class. Okay, so there's lots of different kinds of waves, but all of them we can describe with a few properties. And so if we imagine looking at the displacement of something, I'm just going to call it y, and say if we look at time, so this is displacement as a function of time. This could be displacement along the direction of the propagation of the wave, see if it's a longitudinal wave, or it could be transverse displacement in the case of a wave on a string. But we will have oscillation. Basically, the displacement will increase and decrease in time. And it will trace out, if you graphed it like this, the displacement versus time. Sometimes this is called amplitude. In fact, the difference between the maximum displacement and the minimum displacement is what we call the amplitude. Just to be more precise. Actually, no, we tend to call it yeah, that's better. Half. So it's the displacement from equilibrium. It's the maximum displacement from equilibrium. And so the range of displacements is twice the amplitude. Okay? And the distance over which the wave repeats itself is called the wavelength. And so basically the distance between any point on the wave to another point where it comes back to the same value with the same, call it velocity, is a wavelength. And actually for doing time, sorry, this will be period. Sorry, I forgot we were doing the graph of displacement versus time. at any instant in time, that's when we can talk about the wavelength. So in a graph of displacement versus time, we could talk about this distance, or this interval being the period, and this being the wavelength. So this is like we're looking at a single point on the slinky, and we're looking at the displacement. It goes side to side, side to side. So this is basically displacement at a specific point in space. Well, this is displacement along the wave. So in the case of when we're up here with Colton, I'm calling x like the distance along the table surface. And the y is the displacement either side to side or the displacement of any coil back and forth. Now, from one-dimensional kinematics, remember we had that rate times time equals distance? Well, here, if we call v the wave speed, and t the period, the distance something of a disturbance, a wave will travel in one period is one wavelength. So the relationship between the period, the wave speed, and the wavelength is just given by our one-dimensional motion, rate times time equals distance, with the rate being the wave speed, the time being the period of the motion, and lambda there being the wavelength. That's the distance. Now we can also talk about the frequency. And the frequency is 1 over the period. And so if the period is in seconds, the frequency is in inverse seconds. And an inverse second is what we call a hertz. So basically, 1 hertz is an oscillation per second. And so if we do put that in for our period, we can also write the wave speed as the wavelength times the frequency. So it's pretty much the same relation. And let's do just a quick example. Let's say you're out fishing on one of the reservoirs and you've got your boat anchored right over that hole where you're pretty sure there's some nice big trout. And somebody goes by in one of those personal watercraft. You know the ones, the annoying, noisy things? I'm doing this from the perspective of a fisherman. And they produce a wake. And you get the waves coming in. And so you're fixed on the water relative to the bottom of the reservoir. And let's say you have water waves. And just looking at the distance between the crests, you can see that they're almost a meter. Say 0.90 meters or 90 centimeters. And they pass by. Say you're looking down at your anchor rope, and you can very precisely see when the wave crest passes through your anchor rope, and you get 8 crests in 10 seconds. And so if 8 crests pass by in 10 seconds, any ideas what the period would be? What's the period of this oscillation if the wave crests pass by 8 of them every 10 seconds? Basically, the time interval between each crest. That's what we're talking about. That's what the period is. Anyone want to come up with something? So we're looking right at our anchor rope. So we're looking at a point fixed in space. So we're looking at something kind of like this. We want the period. And we see that the crests go by, 8 of them every 10 seconds. So
would you divide 8 by 10?
no, you don't. 8 oscillations in 10 seconds is, well, 0.8 oscillations per second. That's a frequency. In fact, we could work that out. The frequency is 8 oscillations in 10 seconds, or 0.8 inverse seconds, or 0.8 hertz. That's the frequency. What's the period?
1.125.
Okay, who said that?
Crystal Scheiss.
Okay, and Ms. Smith, that was you?
Yes.
Yes.
She's
Yeah, the period is the time interval. So that would be 10 seconds per 8 oscillation, or 1.25 seconds. Where the OSC is my abbreviation for oscillation. Or you can just leave that out. It's basically just 10 seconds divided by 8, or 8 divided by 10 seconds. Really, oscillation isn't really a unit. And so the wave speed is going to be, well, we could take it as the wavelength times the frequency, or as the wavelength divided by the period. Either works. In either case, if you multiply through this, you should get 0.72 meters per second. So that's our 0.9 meters divided by the 1.25 seconds, or it's our frequency of 0.8 hertz times our wavelength of 0.9. In each case, we get 0.7 0.72 meters per second, so almost a meter per second. Okay. And Colton, can you help me out with this one? So here we have a nice long spring, and just head that away with it. And I don't know if this is going to show up well on the L camera. I'm going to adjust it, so you just hold on to that end. I can do a wave pulse on here. And you can see this is a transverse wave. And we have some friction here, so the wave damps out in a little bit of time. That's because of friction, but there's not enough of it so that we don't have an oscillation. Clearly, there's a disturbance going back and forth for a while. Something else to note, in that when I do an up pulse, when it hits Colton, it turns into a down pulse. That's because of basically conservation of momentum as well as Newton's third law. Because when the wave disturbance gets to Colton's hand, it pushes his hand up, his hand pushes the spring down, and that's what essentially creates a wave going back the other direction. Now, we also have a property of waves called superposition, in that if we have multiple waves traveling over the same medium, where they interact, well, the amplitudes add. So let's see, I'm going to try to do, Colton, just hold still. I'm going to try to do a down pulse, which will turn into an up pulse once it bounces off of Colton. And then I'll follow that with an up pulse. So hopefully, if I do this right, we'll have two up pulses, basically humps, coming together. And I want you to look at their amplitude where they cross. Was that kind of fast, or did you see them kind of add together and get a little bit higher? And if I do two up pulses, well, what bounces off of Colton first will turn into a down pulse, and the two will probably cancel out where they cross. So we get this superposition. So the displacements that each wave would create add together. But something else to note is that the waves, the disturbance, don't interact with each other. They just pass right through each other. A common misconception is that waves, when they come together, somehow interact and bounce off of each other. That's not what happens. Imagine how difficult would it be for conversations, say when people are in a room and multiple people are talking, if your voice actually bounced off the sound produced by other voices, by other people. That's just bizarre. It wouldn't happen. That's not how sound behaves. Your voice will bounce off of walls and surfaces, and you can get echoes, reflections, but the sound waves pass through each other and they don't interact with other sound waves. And a good way to show that is with the Lycra rope. Braden, have you ever done Lycra rope yellow?
Not personally, I don't believe.
Okay, Colton, I'd like you to head down the aisle.
Okay.
And grab that end. I actually got the idea for this from a theater group, and I even talked to some performers. That's good right there. You want to lay this down flat on the ground? And asked them what rope they used and how they made it. And they basically took some long Lycra and rolled it up into a tube to create a rather nice thing. It's fairly elastic, so it's kind of like a spring, but the wave speed is really, really slow, so you should be able to follow this okay. So I'm going to produce an up pulse, and that's a lot slower than what we had on the spring. Okay, now Colton, I want you to try to do an up pulse too. That's actually pretty good. Now, I'm going to make mine really large, and Colton, you make yours kind of small, so we hopefully can keep track of them.
Simultaneously?
Yeah, so we'll do it about the same time. I'll do a countdown. So what you want to watch for is the big pulse and the small pulse. Colton's going to produce the small pulse. I'm going to produce the big pulse. And my big pulse should continue on to Colton after it passes through the small pulse, and Colton's small pulse should continue on to me. They're not going to bounce off of each other. But watch where they cross. We should get the two amplitudes adding together. Okay, you ready? 1, 2, 3. Okay, your small pulse needs to be a little bit larger. 1, 2, 3. Did you see it get quite a bit taller? Both two pulses are about the same size, and we should see like a medium-sized pulse, a bit larger than what you just did. And we should see the amplitude get really big right where they cross. 1, 2, 3. Did you see that shoot way up? Okay. So this is what we call superposition, in that waves pass through each other. They don't bounce. And it's the amplitudes that add. So this is where I'd like to go with the next slide.
Okay.
On that PowerPoint presentation. Okay. So we have square waves. These are what you might see on an oscilloscope when looking at TTL. Oh, do I even want to talk about that? Okay, certain electronics, digital electronic signals actually look like this. So we've got signal 1 and signal 2. And the question is, if they are superimposed on each other, not crossing, going in opposite directions, but they're both moving in the same direction, at that snapshot shown, what would their superposition be? If at that snapshot shown with these two waves going in the same direction, what would their sum be if those two signals were superimposed on each other?
If it's taken at the snapshot shown, then does it matter which direction they're going?
No, it doesn't, just as long as it's the same direction. And we're basically just looking at a snapshot, an instant in time. So does it look like figure A, figure B, figure C, or figure D? That's what I want you to think about. Once you've got your mind made up, get your cards ready. That'll kind of give me an idea of when we can call a stop to the pondering. Okay, it's looking like most people have cards ready. So go ahead and show me your cards. Folks, hit the chat. Okay, what's it look like on the chat?
4 C's, 5 C's. 5 C's so far.
Anything else besides the C?
Nope.
Could I get a volunteer to defend why C is the better picture? Anyone? Could you move that so people can actually see what C looks like? Thank you.
I could go.
Okay, please do.
So looking at the pictures, because they're like the same length, I was just thinking that it would have a higher amplitude when they superimposed, so it would get taller, which is why I didn't choose B, because it just got like wider. I thought it would go taller instead of doing the inverse, which is D.
That's where, right at the end of the second pulse for wave 1, and right at the beginning of the second pulse for wave 2, is where you're saying that the amplitude should add, so that should give us a higher thing.
Yeah.
Okay, that's in fact exactly what's going on. So that's actually pretty good. You're following this really well. This is what we mean by superposition. The amplitudes add together. And what was my next question was was this. Let's hold off on that for a bit. So I'm going to need your help again, Colton. In that, with this superposition, actually, no, let's do this lengthy thing first. We have time? Okay, let's try it. So if you could go down the aisle, down there. Yeah. Okay, we're both going to want a few pulses off to the south. Can you try to do it? Yeah, like that. About that size. but let's try to time it so that our pulses cross somewhere where those cans are. Let's get the slinky kind of straight. Okay, so 1, 2, 3. Okay, not quite enough. We need to be more aggressive. 1, 2, 3. So where they crossed, we have a larger amplitude, and that knocked the cans out. But where they weren't crossing, they didn't knock the cans out. Okay, superposition. Now let's go back to this spring. Go ahead and take that in. And not so far this time. Come closer. Yeah, right about, right about there. Okay, so just hold on to your end of the spring. If I send multiple pulses down, they're going to interact with other pulses I might send down. But if I can send pulses down just at the right rate, so that we always get whatever bounces off of Colton constructively adding to what I send down, that means I have to time it just right. We can get what's called a standing wave. And this is a sort of vibration you get in stringed instruments when you pluck them or strum them. And the distance between Colton and I, imagine this as being part of a larger wave. This is exactly 1/2 of a wavelength. It's basically the distance between one node and the next node. So if you look at the graphs I have on the blackboard, a period or a wavelength is basically either the time or distance between crests in the wave. And so looking at that second one I draw, where we have the distance, the horizontal distance between two crests as being a wavelength, well, you're seeing one up hump. A full wavelength would have another down hump. In fact, if I double the frequency, move my hand up and down exactly twice as often, now we have 3 nodes. One at my hand. Try to hold your hand still, Colton. Yeah, we have 3 nodes. One at my hand, one at Colton's hand, and one right in the middle. And 2 crests. One is up and one is down. And so this distance is exactly 1 wavelength. This is called the second harmonic. With the lower frequency one, 1/2 that frequency, this being called the fundamental. In music, going from this frequency to this frequency is exactly 1 octave. Okay, and I can go to higher frequencies. There's the third harmonic, where now we have 1, 2, 3, 4 nodes and 3 antinodes and 3 crests. So it's 1.5 wavelengths. And we can go on with this. But you note that in order to have the same tension, we have pretty much the same wave speed. In all these cases, we had pretty much the same wave speed. So to get the different wavelength, I had to change the frequency. And if I made the spring, don't move. If I made the spring tighter, the speed of waves are going to be increased. Because the restoring force, the tension, which is the force that's bringing the spring back to its center, which it's back to its equilibrium, is increased, it's stronger, so we're going to have more acceleration with that greater tension. So a greater acceleration means you're going to have a more rapid return to equilibrium. And that means the speed of our disturbance increases. And so our fundamental is now a more frequent oscillation than it was before. In contrast, if I make this really loose, much loose, don't move, much looser than it was before, we have the same wavelength, but now we have a much lower frequency of oscillation. I really think this would have been better served if the camera was far away. I don't know if that's showing up really well on the OWL camera.
It is showing up.
Okay, but I think folks in class are getting a much better view of that. So, as you can know on a guitar, The tighter the guitar string, the higher the pitch, because that means the faster the oscillation. The more frequent the oscillation will be at the fundamental mode. Also, if we change the mass of the string, if we make it heavier, well, we've added more inertia to it. For the same tension, the same returning force, more inertia, would that give us a lower frequency of oscillation or a higher frequency of oscillation? Anyone? What would changing the mass of the string do? I'm seeing some fingers. Could you speak up, ma'am?
Lower it.
Lower it. What's your name, miss?
Mackenzie Robbins.
Yes, that's exactly what would happen. It would lower the frequency because you have more inertia. The acceleration would be less for that same force. And so there's a number of things going on. That's also why, if you look at guitar, the lower note strings, the lower frequency strings, are thicker and heavier and have more mass to them. The ones that are higher frequency are very light, not nearly, well, they're a lot less metal, a lot less mass. And so their vibration is quicker for the same distance. And as you put your fingers on the frets, you're basically changing the length of the string that can vibrate. You still have the string vibrating above it, but you're kind of forcing where a note is, and the biggest oscillation will always be in the fundamental mode, where you have a half wavelength between two notes. And so the longer that string is, higher up you fret, the lower the note you get. The closer to the soundboard you get, where you do your thing, the shorter the wavelength and the higher the pitch. So this can help explain a lot of musical instruments. And this is a good time to get out the yarn. I'd like everybody to pick up the yarn that you have on your tables. And what you want to do is, I need a piece. Colton, can you, I want you to wrap one end around a finger and another, not quite an arm's length away, around your other finger. And put one finger, and don't put it in your ear, put it right next to your ear, or right in front of your ear. And this is horrible with a shield. Okay. And then holding it tight, or at least loosely, pluck it with your thumb. And you should hear kind of a nice strumming sound. No. You want to have a finger touching your head. Touch your head right as close to the opening in your ear as you can. So no, in your ear, not poke it in the hole of your ear, but put it right next to your ear. So that when you, basically, you want a solid contact as close to your mastoid process as possible with your index finger. Am I communicating? And can everybody hear kind of a strumming sound when you pluck it with your thumb? Now, pull the string tighter. What happens to the pitch? It goes up. You've increased the tension. You increase the acceleration of that string back to its equilibrium, and that means the speed of the disturbance, the wave speed, is going to go up. And that gives you, for the same wavelength, a higher frequency. That's what you hear. And if you make it loose, you should hear a lower note. And the vibration should be slower. Did everybody hear that? And for those of you at home, I hope you got the email I sent out about 45 minutes before class. I didn't think of that until just this morning, that we were going to do this activity. And I should have given you more warning, my apologies. But hopefully you have enough time to scrounge some yarn or string. Now, play around with length. Try to keep the tension the same and try a really short length, and then double that length, and then triple that length. And do the plucking. What you're doing here now is you're going with the shorter string, you're basically changing the fundamental frequency. You're changing the wavelength of the string. And as you make the wavelength longer, the longer string, you hear a lower note or a higher note if you make the string longer. A lower note. If you make it shorter, you should hear a higher note. We saw that on the spring. The shorter the wavelength, well, and you can see it from the relationship here, if the wavelength is smaller for the same wave speed, meaning the same tension, well, you should hear a larger frequency. Does everybody feel that? Now, one thing, and this is a bit challenging, you want to twist your yarn and pull out one or two strands. This is a multi-ply yarn. So twist it the wrong way. And I got one strand. You could take off either one or two. This is 4-ply. And you want to try to do this not really, really quickly because you don't want to completely tangle this. And the whole mouth trick isn't going to work.
Yeah, I hope that's.
Yeah, I'm used to grabbing this one end with my mouth. Maybe if I use my foot. Yeah, provide a little bit of tension.
Good.
Okay, so I've got a single ply and I've got 3-ply. And you might have 2-ply and 2-ply. But what I want you to do is now that you have a lower density string, try it. You should hear, for about the same tension you had before, a higher pitch because there's less mass. And for the same tension force, you should have a greater acceleration back to equilibrium, which means the disturbance will travel faster. I want everybody to give that a try. Colton, could you cut out some more string? One more per person. We want to do something else. Has everybody had a chance to play around with a string with different density than what you had before? Okay, now I'd like everybody to have one of these spoons or other gizmos or a coat hanger. And what I want you to try to do is to put your yarn through.
A thick one or a thin one?
It doesn't really matter. In fact, trying it with both would be kind of cool. That's why you have both. And wrap it around both fingers. Put both fingers near and near. And this, you want to stand up and you want to be able to whack the spoon on something and hear the sound you get from that. But then you'll notice a different frequency traveling through the yarn. So could you pass out this and coat hangers? And try with a coat hanger as well. And you don't want it touching you. So you want to be leaning over so that the spoon and the yarn don't touch anything. They're just free to oscillate. And you'll find that the speed of sound through the string is different than the speed of sound through the air, and so you hear a different pitch. Do you hear a lower pitch or a higher pitch? Lower pitch. That tells you that the wave speed travels through this string a little slower than it does through the air. And the coat hanger in particular sounds really boring in air, but once you change the speed of the sound, you get a noticeably different pitch that's a bit more pleasing. Who's tried it with a coat hanger? Did you hear a lower pitch or a higher pitch?
Higher.
Okay. It's actually kind of hard to tell because it's really not a very pleasing sound in the air. It's really not a loud vibration at all. You get a much louder vibration through the yarn.
So if it's like a dull sound, would that mean it's?
Sorry?
So if it's like a dull sound, does that mean it's like a lower pitch?
It means you're not really hearing it well. I frankly heard it at a lower frequency than what I heard it in the air, but the problem is, it's not very loud when you hear it in the air. Okay, that's all the time we have, folks. Again, since we had manipulatives today, be sure to use the hand sanitizer and wipe down your area. Go ahead and throw away the yarn. We're not going to use that again. Discard it. And just have the spoons at the end of the aisles, and Colton or AJ will pick those up for you.